In this section, we're going to look at the two-sample t procedures. We have a two-sample t hypothesis test and a two-sample t interval when we're looking at comparing the mean between two populations. So we would use these procedures that we're going to talk about when we have two separate populations and we take samples from each and we want to compare the population means, the unknown population means using the sample means. So you would have what you have on a normal t-test. You'd have the parameter mu, your sample mean x bar, your sample size n, and your standard deviation s, but you would have that from two different groups, so we can put subscripts to identify which ones correspond to each group. So that's the setup that we have, and we can do hypothesis tests or confidence intervals. And to do either of these things, the assumptions that we need in order to carry these off are pretty much the same as what we had for the one sample procedures, except we have to extend those to both of the samples. So from each of our two populations, we have to take simple random samples, and they need to be independent from each other. So matched pairs, we wouldn't use the two sample procedures. In matched pairs, they're not independent. You can match them up, and we subtract it and use one sample procedures. But for the two sample procedures, you have to have two independent groups. And both populations should be normally distributed, or we know if we use large enough sample sizes that the mean is going to smooth out, and we can use the t procedures if we have large enough sample sizes. And then, of course, there's the assumption that the population means and standard deviations are unknown. We're interested in what's going on with the population means using our samples, and we don't have the population standard deviations either, so we have to use the sample standard deviations, which is why it's t procedures. There are two sample z procedures, but I never cover those in my classes because in reality, in real life, you would already be using the t procedures. They would be more accurate or more realistic because you never know the standard deviations if you don't know the means. So whether or not we do confidence intervals or hypothesis tests, in either way, we have to have some sort of measure of our statistic that we're looking at. And in the two sample case, our statistic is the difference in the means. Well, our statistic would be from the sample, the difference in the x bars, the sample means. And our parameter that we're interested in is the difference in the population means. In most cases, whether or not that's zero or if one is bigger than the other. So it's basically a combination. Excuse me, the procedures are going to be similar to what they are for the one sample, but the way the formulas are computed are a little bit more complicated because we have the two samples put together. So the standard deviation that we would use in this case would be this combination of the two. It's the standard deviation of our statistic x1 minus x2 bars would be the square root of each sample standard deviation squared, or the variance, divided by the sample size. So you have the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And because we don't know sigmas in this case, we use s's instead, so that's our standard error. If we look at the square root of s1 squared over n1 plus s2 squared over n2, that would be the standard error of the difference of the two means. And so our test statistic, if we were going to do a hypothesis test, remember the general form was, for the one sample, we had our statistic minus our parameter over the standard deviation of the statistic. And so in this case, our statistic is x1 bar minus x2 bar. Our hypothesis is that the difference in all cases when we do this, our null hypothesis is going to be that mu1 equals mu2, or mu1 minus mu2 equals 0. So on top, we have our statistic x bar 1 minus x bar 2 minus 0, so we don't have anything else on top. It's really just an implied minus 0 here. And then divided by the way we're measuring the standard deviation for our statistic, which is this big square root with the combination of the standard deviations and the sample sizes. So that's the two-sample t statistic. It has approximately a t distribution. And the degrees of freedom is now much more complicated. If you didn't have technology or tables, which you should have access to technology, but if you didn't, a conservative approach, meaning that if you find a significant result, it definitely is significant, but you lose some power when you use this, would be to use the smaller of n1 minus 1 and n2 minus 1. Remember, for the one sample t-test, your degrees of freedom is n minus 1. Here you have two samples. You could do n minus 1 for both of them and then take the smaller. That would be the conservative approach. A much more accurate approach would be to use software to compute this kind of monster of a formula we see here. You can do it by hand, but software can do it very quickly. So the t-distribution of that two-sample t statistic for x1 bar minus x2 bar, it's very close to a t distribution with this degrees of freedom, this big combination of the sample sizes and the standard deviations. And they say this is a good approximation we can use in relatively small cases when both sample sizes are at least 5 or larger, that this is a fairly accurate measurement of the degrees of freedom. So we can do confidence intervals and we can do hypothesis tests.